In this Mathematica Sessions video on Discrete Maths, episode 8 of this series, we're going to look at relations, and that is equivalence relations, partial orders, and total orders, and equivalence classes. So if that's what you're interested in today, then keep watching. Welcome. All right, so it's time to start. So I'll go ahead and start. Can you guys hear me okay? I'll ask someone. Yeah, that's good. Thanks. Great. So I still don't know how to open the chat. So I'll have to rely on your thumbs up or your audio. If you've got any questions, please just turn your mic on and just ask it. That'd be great. Okay, so let's begin this. Now we've got 5 questions overall on this problem sheet, and they're about relations, and that is equivalence relations and partial orders and total orders. Okay, so let's have a look at our first question. So the first one, we're given a set A, and that's got A, B, C, D, and E in it, and then we've got a relation. Now remember, a relation is a subset of the Cartesian product of A with itself. Okay, so for example, if we see A comma B in the relation, then that's saying that A is related to B. All right, so now that could be something like friendship, for example, right? Suppose Roy is friends with Sachith. Then Roy comma Sachith would be in the relation of a friendship, just as an example. Okay, so our first question about this particular relation here is, well, to draw a digraph. Okay, so since I'm not working with drawing tools here, I've just written some code to do that. And it's just below. So this is Mathematica code. Of course, you don't need to know anything about this code or doing that yourself, but it does make a nice, pretty diagram with very little work. So basically what I've done is I've entered the relation, and you can see I've used the set brackets here just because that's the way Mathematica likes to input arrays, and so I can index on them, pulling out specific elements. So I'm doing that with this command right here. I'm pulling out the jth element and then the first element of the jth element. So if, for example, this B comma A is the jth element, then the first element of that would be B. And likewise, this is the second element of the jth element. In this case, it would be A. All right, and so this little symbol here says basically to draw a directed graph or an arrow basically from the vertex. In this case, it would be B to A, right, for this particular value. And that's what, J equals 7. And then I just make a list of that with this command table up to the length of the relation. And then I say to graph that and to label the vertices by the name of those vertices. Okay, so I'll take the semicolon off and I'll show you. So here we see the first part of it, but there's more. So I'll scroll down and show you more, and I'll just resize this to make it a little more manageable. All right, so what we have here is that we see that B is related to A is related to B, B is related to D, D is related to B, and so on. And these little arcs, like B going to itself, that represents this one right here, B related to B. Okay, now we've got another section of this, right? Because there are no connections from the A, B, D collection to the C and E collection. So that's why these are disjoint as graphs. All right, and you can see that in the relation itself, right? There are no such connections from A, B, or D to C or E. Okay, now for the next part of it, I think we need some definitions. All right, so yeah. So is it reflexive, symmetric, and transitive, and give reasons? All right, so we need definitions of these, which you've probably already seen, but I've got them here just to make this convenient for us. So reflexive means for all x belonging to A, x is related to itself. All right, and you can also write this x row x. So geometrically or on the graph, what this means is that every one of the vertices has a loop on it. And so a loop is an arrow that's going to itself. All right, now this is the case here. We see it for all of these vertices. We have a loop going to itself. And so for that reason, we see that the relation is reflexive. Any questions at this point, guys? All right, thanks, Jeremy. So good. Now, symmetric. So symmetric means if you have x related to y, you need to have y related to x. Okay, so in terms of the digraph here, whenever we have an arrow from one going to the other, we've got to have that arrow going back the other way too. Okay, now you could have an isolated vertex with nothing, and that would not interfere with the symmetry, right? Because remember, it's an if. So in other words, if we had an F out here, somewhere here, and not connected to any of these other letters by an arrow, that would still be symmetric, right? Because in that case, F is not connected to any others, so there are no arrows going one way, and so therefore you don't need any arrows going back in that case in order to be symmetric. Okay, transitivity, transitive. If X is related to Y and Y related to Z, then you need X to be related to Z. Okay, so I like to make an analogy. If Roy is friends with Jason and Jason is friends with Sachith, does that mean that Roy is friends with Sachith? Well, the answer is no, right? Because if you've experienced friendship, then you know that friendship doesn't necessarily work that way, right? Roy might really like Jason. Jason might really like Sachith, but it might also happen that Roy doesn't like Sachith for whatever reason. Sorry, Sachith. You're probably very likable. Okay, so friendship, I would say, is not transitive, but so this is what it means, and usually it's the most difficult thing to prove when you're trying to prove an equivalence relation. Now, an equivalence relation is a relation in which you have each of these satisfied: reflexive, symmetric, and transitive. Okay, so let's have a look at the next one then, which is double I, which says, is rho an equivalence relation? So let's have a look. Is it reflexive? Yes, we've already decided that. Yes, it's symmetric because the arrows go both ways for each of them. Is it transitive? Yes, it's transitive, right? Because whenever B goes to A and A goes to D, B then goes to D. And that happens everywhere, right? And so it takes a lot of checking to deduce that it is transitive, but in this case it is. So we'll say yes, reflexive, symmetric, and transitive. All right, and for the reasons of these definitions here. Okay, now, given that it is, can we give the classes? Now, whenever you have an equivalence relation, it then partitions the set A into classes, okay? So things that are related to each other are in the same class. All right, so if you just look at this, the fact that you see two disjoint sections of the digraph, that means here we see two classes. So A, B, and D are related and to one another, and C and E are related to one another because there are connections there between them. So the classes then are A, B, D, and C, E. Okay, so let's just note that. And I'll copy paste here. So rho is an equivalence relation since reflexive, symmetric, and transitive, and the induced equivalence classes are, what did we say, A, B, D, and the other one is C, comma, E. All right, and whenever you have a class, you can represent that with a square bracket. So like A, for example, represents all of the elements in A, B, D, right? And so you would say then that square bracket A is the same as square bracket D because those belong to the same class. Okay, but square bracket A is not equal to square bracket C because those are in different classes. All right, any questions, guys? All good so far? Great, okay. So with the same set A, what is the smallest subset tau of rho which forms an equivalence relation on A? All right, so let's just bring up rho again. So I'll just grab this that's nearby. So this is what rho is, right? And now if we're taking a subset of that and we need it, we need the smallest such subset, meaning how many elements in it, such that this is still an equivalence relation. Well, remember, we've always got to have elements related to themselves. In other words, it needs to be symmetric, right? And that has to happen for all elements x of A. So I'll just write that. For all x in A, we require x comma x to be in the relation rho. In other words, this is the reflexive property, right? So that means that tau, the smallest subset, has to have all of these in it, right? So let's just copy paste here. We've got AA that we need. We've got BB, CC, DD, and we need to have EE. Jeremy, I can hear you. Do you have a question? Just speak up if you do. All right, so we've got to have at least these, but is this an equivalence relation? So it's reflexive. It's symmetric also because we don't have any connections. These are just isolated loops, right, from each vertex to itself. So remember, we have the if condition on symmetric, right? So since we don't have any arrows at all going from two different points to each other, then symmetry is satisfied. Okay, and likewise, it is transitive. So this is the smallest subset that is still an equivalence relation. And you can see I'm abbreviating this to make it faster. Okay, let's have a look at the next one. That completes question 1. I'm going to press save here. All right, great. So next, we've got a set. X is 1, 2, 3, 4, 5. The relation R is a subset of the Cartesian product X with itself. And the relation's given by this 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, 2, and so on and so on. And then we've got some questions. Write the inverse relation. Okay, so in the inverse relation, what that means is if 1 is related to 2, then in the inverse relation, I have 2, 1. So I basically have to reverse every pair. Okay, so this is easy to write then. our inverse is, and I'll just take this and we'll manually just reverse all of these. So 2, 2, 3, 3, all those are already fine. Now these, that becomes 2, 1, then we have 3, 2, and 4, 3, and 5, 4, and 1, 5. Okay, so this is the inverse relation. Now, next question, is R symmetric? Is the inverse symmetric? Is the union of R with its inverse symmetric? And explain these. All right, so first, is R symmetric? Well, no, it's not, right? Because 2, 1 belongs to, I'll just put in rather than go and find the symbol, is in R, but 1, 2 not in R. So not symmetric. All right, now what about the inverse? It's the same story, right? So I can just copy and paste this and say 1, 2. Oh, hang on, I've got this the wrong way around because I was looking at this. But what I need is, no, that's right. No, it's wrong. Okay, so R is this one up here. Okay, sure. Okay, so 1, 2, but not 2, 1. There we go. And then now I can look at this one. So 2, 1 is in our inverse, but not 1, 2. So our inverse is not symmetric. Sorry about that. Okay, anyway, so what about the union? Now the union is also not symmetric. Since, now let's just choose some. How about 1, 2, and 2, 3? Okay, so 1, 2, and 2, 3 are in this union. But what about 1, 3? 1, 3. Let's see, it's not there, right? It's not in that set, and it's not in this set, so it's not in the union. Okay, so 1, 3 not in the union of our inverse. Not symmetric. All right, good. So I think we're ready for the next question here, unless you have any questions, guys. Now the next one said, yep.
Where does the 1, 3 element from?
What is the 1, 3? Is that what?
Yes, I'm not sure. Yes, where can we find 1, 3 element?
Okay, so now, so 1, 2 belongs to R, 2, 3 belongs to R, so that means that it belongs to the union of R with R inverse, right? Because that means in R or in R inverse. And so this is the case. Do you agree?
Yeah.
Yep, okay. Now this one, this is not in R, right? Because it's just not there. And it's not in this one either. It's not in R inverse. It's just not there, right? So that means that it's not in R union R inverse. Do you agree?
But where does 1, 3?
How did I come up with it? Oh, I see.
Yeah.
Right, okay. So this here says, I mean, if we go and look at the definition, so I'll copy and paste the definition down here of transitive, right? So where were we? So definition of transitive says that if x comma y is in the relation and y comma z is in the relation, then we require x comma z to be in the relation. So in other words, I'm just seeing that these are the same. The 2 is the same as that 2. And so I require that 1 comma 3 be in the relation. So that's how I got it. Do you follow that, Jeremy?
Yeah, but we didn't say that R or R inverse is a equivalence relation. We are just talking about symmetric. So
Yeah,
what we are,
we're simply just checking whether it's transitive. Oh, right. Sorry, symmetric. I was thinking transitive. All right, I see the problem now, Jeremy. So sorry, because this is about symmetry. So what I need to do here is take this, because that's the next question, really, right? Okay, so I'll put it there in the next question. Yeah, and sorry, somehow I got confused. Okay, so 1, 2. So I need to get rid of this part and find one. And actually, this is symmetric, right? Yeah, it's symmetric. So it is symmetric. Right, but the reason we have to say is a little bit different now. Since if x comma y is in R, then y comma x is in R inverse, right?
yeah, that
So
makes sense.
that means
Yes.
then, so if x comma y is in the union of these two, then y comma x has to be in the union because it's in the inverse, right? So it's in this union. All right, sorry about that. Somehow I was just thinking ahead and thinking we were talking about transitivity, but we're not yet talking about transitivity. All right, so thanks for letting me know about that. Okay, great. So are any of these transitive? So how about R first? So we've already worked out that R union R inverse is not transitive. So change that to transitive. And I'll move the definition up. All right, but what about R? So, so when we have 1, 2, and 2, 3, we don't have 1, 3. Okay, so we'll say R is not transitive. Now the same would go for R inverse, right? So R inverse also not transitive. And the reason why would be, if we look at R inverse, let's see, we've got 1, 5, 1, 5, and 5, 4. In the inverse of R, but not 1, 4, right? Okay, good. So not transitive. So none of those are transitive. All right, have I got this correct, guys? I think so. All right, thanks. Okay, so let's move on and look at question 3. All right, so rho is a relation on the integers given by x related to y if and only if, and I'll abbreviate if and only if by IFF, if and only if x squared minus y squared is even. Okay, so we've got a few preliminary questions about this. It says, is n squared even or odd? So what we mean here is, can you tell whether n is even or odd based on can you tell whether n squared is even or odd based on whether n itself is even or odd? And the answer is yes, that they have the same parity. Okay, so first, if n is even, then so is n squared, right? So n squared is even. And that's easy to prove, right? You just say let n be equal to 2m, and then you square it, and you get 4m squared, and you see that 4m squared is even. So also, if n is odd, then n squared is odd. So n and n squared have the same odd-even parity. Okay? And that allows us to more easily look at the second question in this question 3, right? Because since x and x squared have the same odd-even parity, and the same with y and y squared, that means that if x is odd and y is odd, then this difference is odd, right? And likewise, if, even, then the difference is even. So in other words, if both x and y have the same parity, then this result is even. Okay, so we just have to check in each of these cases, is 3 the same parity as 2, right? And the answer is no. So I'll put false for this one. And then this one, no, these are not the same, so that's false as well. Now the next one is 2 row 4, so those do have the same, they're both even, right? So this one is true. 3 row 3, yes, that's true because they have the same oddness or evenness. Now the last one is false because 101 is odd, but 1000 is even. All right, any questions? Okay, sure. So prove that rho is an equivalence relation. So we've got to show that it's reflexive, symmetric, and transitive. So let's start with reflexive here. So, and I'll just go with x row x, right? And so I'll just pull up row x, and that'll be reflexive. So we'll do this one by one. Reflexive x row x is true since x squared minus x squared is 0, which is even. All right, now symmetric. So if we have x row y, then what we have is we have x squared minus y squared is, say, 2n, where n is an integer. Okay? And what that means then is, so multiplying by minus 1, we then have y squared minus x squared is 2 times minus n. Okay, and so you can say hence, since this is even, we have y row x. So y row x. Okay, so it's symmetric. All right, now let's look at the last one, transitive. All right, so this is a double assumption here. So if x row y and y row x, then what we have is x squared minus y squared is even, okay? And, oh, hang on. I've set that up slightly off, so that's meant to be a z, right? And we also have that y squared minus z squared is twice, say, m, where m is an integer. Okay, now let's just line these up to make this look a little clearer, right? Because now you see all I have to do is add these two equations and the y squareds will vanish. Okay, so next we'll say adding the equations. Then what we have on the left is x squared minus z squared. So x squared minus z squared, and then what we have on the right is 2n plus m, but we can express that as 2 times m plus n. Okay, which is even. So what we've shown is that if x row y and y row z, then x row z. So x row z, and it's transitive. Okay, guys, questions? No, all good. Thanks, Jeremy. All right, so next one. Hang on. Next one, what are the classes? Well, that's easy, right? The classes are just evens and odds. So I'll just write this as a set. So, and then I'll just write uppercase as a set, the set of even numbers, and the set of odd numbers. So these are the classes, right? And so what that says is that 2 is equivalent to 4, and 4 is equivalent to 6, and so on. All right. Hi, Griffin. How you going? Good to see a friendly face there. All righty. So let's have a look at the next one now. So question for us, basically to fill out a table here. And what we've got are reflexive, symmetric, antisymmetric, and that's a new one. And then transitive, and do we have an equivalence relation? Right, but we've got 3 relations, alpha, beta, and gamma. Okay, so they're defined as follows. So the underlying set is the integers, but x is related by alpha to y if and only if x plus y is even. Okay, and then we've got some others here, but let's look at these one at a time before we fill out the table. All right, so first we'll look at alpha. And so is alpha reflexive, symmetric, transitive? So let's start with reflexive. So reflexive. All right, do we have x alpha x? So x alpha x, yes, we do, because, so we'll say since x plus x is equal to 2x, which is even, okay? So alpha is reflexive. All right, what about symmetric? Okay, so symmetric, if x alpha y, then what we have is x plus y is even. So we'll write x plus y is equal to 2 times n, where n is an integer. Okay, but if that's the case, then what about the other way around? So yeah, we can just swap this around because we have commutativity of addition. Hence, y plus x is also equal to 2n, right? Because we just swapped the x and y around because addition is commutative. And so that tells us that y alpha x. So y alpha x. Okay, good. So it is symmetric. All right, now what about transitive? If we have x alpha y and y alpha z, then what we have is x plus y is 2n, and also y plus z is even as well, but let's call it 2m. Okay, and now what about x alpha z? All right, so to do this, again, we can add this, right? So it's a little bit tricky to think of. How do we do this? So let's just line these up as simultaneous equations. Okay, and I'll just say adding these, what we have then is x plus 2y on the left plus z is equal to twice m plus n. And so let's notice here that we've got an even coefficient there. So we can really express this as x plus z is twice m plus n minus y. And so we see that x is related to z because x plus z is even, okay? So which is even, and so it's transitive. So transitive. Okay, any questions? All right, so given that, I know now that alpha is an equivalence relation, so let's go ahead and fill out this table, but you can see we're not quite done because we've got to consider antisymmetry as well, but you need a definition for that. So it's reflexive, symmetric, transitive, and that makes it an equivalence relation. Okay, but what about antisymmetric? So I've got that definition here. So let's do that for alpha. All right, so the definition is for all x and y belonging to the set x, if x is related to y and y is related to x, then you need to have x and y equal. Okay, so is that the case for the relation alpha? Okay, so let's have a look. If we have x and y related by alpha, and the other way around, so let's write assume here. So assume x is related alpha and y is related to x, sorry. So y related to x via alpha. Then what we have is x plus y is 2n. But notice that's just swapping those around. So we also have and y plus x is equal to 2n. Okay, but does this mean that x is equal to y? And the answer is no, not necessarily. But we don't necessarily have x equal to y. All right, so it is not antisymmetric. Okay, so let's just talk about the term antisymmetric. It's a little bit misleading. It doesn't mean not symmetric. It has a different definition, okay? So it has this definition. So don't be misled by the words there. It doesn't mean the opposite of symmetric. Okay, so let's go ahead and tick no for that one. And then you could fill out the others as well. I think I want to leave that for you guys to do on your own, just to make sure we got enough time to go through the rest here. So, unless you got any objections. Okay, so by the way, Griffin, if you're new around here, feel free to turn on your microphone and say anything anytime you want to. Anytime you've got a question, just go ahead and speak.
Yeah,
yep.
I'm a flexible student. I just want to review.
Okay.
Thank you.
Sure, no worries. All right, so now, basically the next one says, for each equivalence relation, what are the equivalence classes? All right, so we've only done alpha here, right? So, righto, so alpha, x plus y is even. How does that break up the set of integers into classes? Okay, so basically if they have the same parity, right? So in other words, this is just evens and odds again. So evens and odds. And I better write that this is for alpha. Mohammed, you can keep your camera on. That's okay. In fact, I feel it's more natural the more people who have their camera on, right? It's good to see some faces. I can see how you're reacting, and sometimes if I see you guys frowning, that means I didn't explain something correctly.
I just thought that I'm lying in my bed, so it doesn't be considered rude that I'm not sitting in a chair. So.
Oh, no, it's fine. I can see you in the bed. That's perfectly fine. So long as you've got clothes on, that's good. Yeah. All right, so I should write classes of alpha, and I'll just write out alpha are these two. Okay, all right. Any questions, guys? So we've got one more here. Maybe it won't take so long, and then if we have extra time, we can go up and do a beta and gamma. Okay, so let's have a look at the next one. So rho is a relation on integers, and it's defined by x rho y if and only if x cubed minus 1 is less than y. Okay, so prove that it's a partial order relation, and what this means is reflexive, antisymmetric, and transitive. Okay, so don't confuse that with an equivalence relation, because the difference here is antisymmetric in the second one. So we've got to have these three properties for it to be a partial order relation. Now for this one, it's a little bit tricky, right? Because we've got a less than symbol. Okay, but let's just walk through this. So first of all, is it reflexive? So reflexive, well, do we have x rho x? So let's try it. So we take this and we replace the y with an x. Okay, is this satisfied? Well, yes, it is, right? So yes, true, since minus 1 is less than 0. Okay, right, great. So that's true. So it's reflexive. So let's go ahead and look at symmetry. Is it? Antisymmetry. Confusing myself with the other one, which is equivalence relation. Antisymmetric, question mark. Okay, so that says, and I'll just copy this, except, yeah, it's still rho, okay. All right, so in other words, if x and y belong to the set, now that set is this time integers. If x is related to y and y is related to x, do we have these equal? All right, so let's try this. So if x is related to y, so we'll say assume this, and we're assuming the other way around, where we replace the y with an x and an x with a y, okay? So assume we have these two. So can we deduce that x is equal to y, okay? Now it's really tricky, but the key here is that this is an inequality on integers, right? So I'll just point out that 3 is less than 5, right? That's true. But this is equivalent to, so this is logically equivalent to 3 plus 1 is less than or equal to 5, right? Because we're dealing with integers. These are integers. Okay, so that's the reason there. So we need to add 1, all right? And so, for example, 3 is less than 4. is the same as saying that 3 plus 1 is less than or equal to 4, right? In fact, in that case, those are equal. Okay, so what we need to do here is say that this is the same as saying that this is less than or equal to this, but I need to add a 1, all right, on that left-hand side. Okay, and let's say which is same as x cubed, and I'll just copy and paste. Same as x cubed less than or equal to y cubed. Okay, now the other way around works just the same. Okay, so this one is the same as, and I'll copy and paste, is the same as saying y cubed minus 1 plus 1 is less than or equal to x cubed, and that's the same as saying y cubed is less than or equal to x cubed. Okay, so now this tells us then, so what we've deduced is that x cubed and y cubed have to be equal, right? Because we've got those inequalities going both directions, and they're less than or equal to symbols. So whenever that happens, you have equality. Okay, so what we've deduced is that x cubed is equal to y cubed, right? Okay, now how do we find out that x is equal to y? So I've got to factorize now, right? So what we want to do next is take everything over to one side of the equation, and that says x cubed minus y cubed is equal to 0. And then I need to factorize the left-hand side. Okay, so I'm just, I know what the factorization is, but I'll just show you here how I can use this computer to do it for me. And you guys can do this in Wolfram Alpha. It's just the same software. All right, so here's the factorization, and now I can copy and paste this right in here and say this is equal to this, and so we have this equal to 0, right? We're almost there, right? Now, if we can only obtain that x minus y is 0, then we're done. All right, but to do that, what we have to do here is show that this is never 0, right? So, but we can just say that. Now, basically, okay, so I'm going to show you in one way here with a computer without me mucking around too much. I'm going to say solve this is equal to 0. Whoops. I have to put a double equals for that. And I'm going to solve it for x. Okay, so I'll get an expression in terms of y. But you see what the roots of this are. They're not only complex, but they've got irrational terms in them. So what we see then is that the factors of this are not integers. Okay, so that tells us then that this is irreducible over the integers. Sorry, I need to take a sip of tea. So what that means is that this is never 0 for any x and y in the set of integers. And so what we have to have is the other one has to be the one that's 0, right? So that says, so this is equal to 0, and hence x is equal to y. So we have found that this relation here is antisymmetric. So and I'll just spell it out. Rho is antisymmetric. Okay, and so since we already know, oh, hang on, we didn't do transitive, right? but maybe we've got enough time to do transitive. All right, so leave some space for this. So it's transitive. So basically, we already know that this means x cubed less than or equal to y cubed, right? So transitive. So if we have x cubed less than or equal to y cubed and y cubed less than or equal to z cubed, then well, we just join up those inequalities, right? And so we see immediately that x cubed is less than or equal to z cubed. And so I can even put this in because that's true, and that's how we got that. So the relation is transitive. So rho is transitive also. So we have shown that rho is a partial order. Okay, good. Now that one was a little bit involved. Better save this. All right, so let's go and look at the last question here. And I'll just press enter so it appears. Is it a total order relation? So a total order relation is a partial order relation, and you have one other thing, right? And that other thing is for all x and y that are in the set x, and in this case it's integers, either x is related to y or y is related to x. Okay, so this is clear, right? So we do have, so yes, we do have either x cubed less than or equal to y cubed or y cubed less than or equal to x cubed. And that's fairly obvious. Because one of those cubes is going to be the bigger one, right? Hang on, I think there's more to this, right? Because we can have both. We can have both as well. And that's when they're equal. Okay, so this definition, I think, maybe is not quite complete. So I think it probably, now you guys could check this in your workbook, but I think, I'll just write I think, x not equal to y, right? Because when x is equal to y, then it's not an either, right? Not an exclusive or. So I think that's what you need to do there. Okay, guys, so I've gone a couple minutes over time, so I think I'll just leave those other ones, the beta and gamma relations, to you guys to do on your own. But let me know if you got any questions now. I see you've got a new assignment available to you to do. So you can ask any questions on that as well if you need some more hints. I mean, I don't want to take up all of your time doing 2 questions if you need some assignment hints.
Hey, Sam.
Yeah.
So I submitted assignment 1 and 2. 2 has been marked, but 1 has not been marked yet.
Yeah, I saw that. And so that seems that I would speculate that either you were late in submitting it or somehow I missed it. Do you know what it is?
So I got an extension, and so my extension was approved. And as for like I was in the extension time, so technically it was not late. I mean, it was late, but it was not late.
Okay, Mohammed. So then no worries. I will go back and mark that, and you'll get a mark. I've also got to go and upload the ones with the feedback, and so.
Yeah, that would be really great. Yeah.
Yeah. So sorry, guys. I'm planning to do that as soon as I can. Yeah, I've been very busy. So.
No worries.
All right. Thanks, guys, for participating. Any more questions?
I got a question when doing assignment 3, and it's like, can you shortly explain what is the domain and codomain when we define a function from Z3 to Z3? And the function is like, for example, x plus 1.
Okay, so domain and codomain. Well, so domain is just by definition, irrespective of what the map is, it's the set on the right-hand side, right? So I could say something like define a map F, and it sends, let's say, X to Y, okay? And then it's given by F of X equals blah, blah, blah. Who cares, right? Doesn't matter. But let's just choose X squared, all right?
Yeah, I know this type of thing. I just not clear about Z3 on Z12 or something, Zn.
Okay, so but I'll just finish here. So this is the domain, and this one's the codomain, right? And so it's just given to you. But maybe your question then is, what is integers cubed? What does that mean, right? And so maybe you're looking at something like,
It's like Z modulo 3, Z modulo 12.
Yeah. Okay, I'll have to look at the assignment. I haven't downloaded it yet, but are you talking about a symbol that looks like this?
No, the 3 is down, is at the right bottom corner of the Z.
Not like that? Okay, so we got 3 possibilities, but what you're saying then is this. Yeah?
Yeah.
Subscript. Okay, now depends on it depends on who's writing it, but I think in this course it generally means this, right? So integers modulo 3. All right, so this is the set of classes where these are congruence classes, set 1, 2, and 3, where these are the equivalence classes modulo 3. All right, so in this class, you've got 0, 3, 6, and the negatives that are divisible by 3. This class contains all the integers that are congruent to 1 mod 3. Sorry, this is a 2. And this one's all the integers that are congruent to 2 mod 3. So 2, 5, is it 7? No, it's 8. 2, 5, 8, and so on. Yeah. Okay. So does that help?
I know each elements in each class, but I'm not sure how to put them into a function.
Okay, can you describe the question in a little bit more detail for me?
All right, define a function from Z12 to Z12, and the function is like
You say 12
Z,
here.
yes.
Yeah, okay.
Z12, and I can remember the function, and let's just an example. I like x plus 1.
So f of x is equal to x plus 1.
Yeah, let's set that as an example. Yeah, and is the function onto or and 1-to-1?
Oh, okay. So you consider what's in this, right? So this is,
Yes. Yeah.
these are the classes just like this, but it goes up to 11, and you're working modulo 12. So then the question is that bijective? So is it injective and is it surjective? So what you have to do is assume that f of x is equal to f of y, and prove that you have to have x equal to y. Okay, and so if you get that, then you find out that it's injective or 1-to-1. All right, and then for onto, you've got to ask, does every element on the right-hand set, does it come from somewhere under the map? Does it come from somewhere on the left? Right?
Yes, I can do this question if we change the question from integer to integer, but I'm confused about this when the question is like Z12 to Z12.
Oh, well, no, it's fine. It's just the same thing, except your elements are the classes of those congruence classes modulo 12. So, for example, let's just choose one. So the class 5 is equal to the set of all x that are congruent, and I'll just put in equals for congruent to 5 mod 12. Okay, and so you can write that. Now this time I mean equality, so x is equal to 5 plus 12k, right, where k is an integer. And so these are the elements, right? It talks about the whole collection of numbers of this form. And it's just as easy to work with, right? As ordinary numbers. So basically, I mean, if this is the map right here, is this the same one as your assignment?
It's not quite similar, but the function is different. But I can remember the original function.
All
so
right.
this is just an example, like
so
x plus 1.
Say something like assume f of x is equal to f of bracket y. And then I have to show that those two classes are the same. So since x is just a representative of the class, then what that really says is that x is congruent. And I'll see if I can find the symbol here just to avoid confusing you. Just, you know, the 3 horizontal lines. That says that x is congruent to, or sorry, x plus 1 in this case, right? Because we're dealing with x plus 1 on the other side of the map, is congruent to y plus 1 mod 12. Right, and you can easily see that x has to be congruent to y mod 12, right? So x congruent to y mod 12. And hence, the classes are equal, right? So that proves that it's 1-to-1 then.
Why the left-hand side doesn't have a mod 12?
Why the left-hand side has mod 12? Oh, no, so this says that these, okay, so you're accustomed to dealing with something that works as a function, right? Now I've got such a thing here. So if I go something like, what is 15 mod 12? Right, it gives me one number, but what it gives me is the least remainder. Now in your notes and in the book by Susan App, this is the way that they treat the mod function, right? But mod in reality talks about a whole collection of numbers, right? So because if I just add another 12 to this, I'll get another number that's congruent to 3 mod 12. So for example, what is it? 27 would be another example, right? So these two have the same mod, but the way I would write this mathematically is I would say that 27 is congruent to 15 mod 12. Okay? So on the one hand, you have a function that gives you the least remainder, but the way we write this mathematically, these two have the same remainder, mod 12. All right, so this is really the way to do it.
Oh yeah, I got it. I thought it was equals to.
Okay.
It's congruent.
Now, so here we see, yeah, because these are congruent mod 12, the classes that they're in, because these are representatives of infinite classes, but these classes are the same class. So here I really do mean equals.